Welcome. We continue our discussion of limits today with section 2.2, definitions of limits. We will see one-sided limits, normal limits, and numerical limits. So, to begin, one-sided limits. Here is the graph of a function, f of x. So remember, when you see the graph of a function, horizontal axis x, vertical axis y, I plug in values for x, and then the function values are listed vertically. So, for example, if I plug in 1, so f of 1, that value, I put in x is 1, I trace it up, and I get the solid dot at 2. So f of 1 equals 2. But what if I go just a little bit to the right of 1? So f of 1.01. Well, if I go just to the right of 1, then the function value is way up about 3. So that's approximately 3. As x approaches 1 from the left, how does f of x change? I'm really asking about the y values. As x approaches 1 from the left, how do the y values of the function change? So let's take a look. Well, initially, from the far left, the y values are up around 2, and then the y values go down to 1, and the y values go down to 0, and then the y values start increasing, and as x approaches 1, those y values get really close to 2. So we would write this way. X arrow 1, 1 with a superscript negative. That means x is getting closer to 1 from the left. And as x gets closer to 1 from the left, the y values get really close to 2. I don't even really care what happens early on in the process. It was 3, and then 2, and then 1, and then 0, and then it climbed again. I only care about the end of the process. The function values ultimately approach 2. Here's how I would write this as a limit. The limit, as x approaches 1 from the left, of f of x equals 2. How about the right? As x approaches 1 from the right, how does f of x change? How do the y values change? So I start way to the right, and they're about 2, and then they go up to 3, and then down to 1, and I'm approaching from the left. Those y values are climbing up to about 3. So it looks like as x approaches 1 from the right, superscript plus, the values of f of x, the y values, approach 3. And we write this as the limit as x approaches 1 from the right of f of x equals 3. Just a quick note, the answer to a limit problem is a y value. Sometimes students get confused about this. The answer to a limit problem is a y value. 2 was the y value that I approached when x went to 1 from the left, and 3 was the y value that was approached when x went to 1 from the right. Here's a problem for you to try. Pause the video right now and look at this graph. This is the graph of a function f, and see if you can answer those two questions. Unpause when you're ready to see the answer. All right, let's take a look at the answer. So as x approaches negative 1 from the left, so here's my negative 1. As x approaches negative 1 from the left, oh, look what's happening to these y values. These y values are constantly 1. They don't change at all. So it just stays 1. They didn't even move. They were constant. How about this? X approaches negative 1 from the right. So what is happening to those function values? The function values go down to 2, down to 1, up to 2, down into negative territory. But those y values ultimately end up at about 0. So hopefully you ended up with 1 and 0 as your answers. All right, now let's talk about the regular limit of a function. Not just the left limit or the right limit, but kind of just the limit of a function. Here's an example of a function x plus 1 times x minus 1 over x minus 1. This is a curious function. I mean, it looks nice and normal. It's just a good straight line, but it has a hole in the middle. If I try to plug in 1 into this function, f of 1, it just simply has no value. It does not exist. And you can see that because if I put 1 into the function, I get 0 in the denominator. This happens more than you'd think in calculus. calculus, we very often have these kinds of functions that have a hole. And our goal is to sort of fill the hole. What should that y value be? And this is where we use the limits. So I approach 1 from the left. As x approaches 1 from the left, what's happening to the function values? Okay, the y values increase up to about 2. And what happens when I approach 1 from the right? The y values decrease down to about 2. And here's the key idea. These match. That is a nice thing. Since the left and right limits are the same real number, that's when we say that the limit exists. The limit as x goes to 1 with no superscript, f of x equals 2. You know, if there's that hole in the graph, 2 is the value that should be filled there. All right, again, I'll pause, try this on your own, see what you think, and then unpause when you're ready to see the answer. In this example, f of 1 equals 3. That's where the dot is. So it has a hole there, so I skip through that, and 3 is the value of the function at 1. But how about this? The limit as x goes to 1. Well, as x approaches 1 from the left, those y values go up to 2. And as x approaches 1 from the right, well, the y values oscillate. They just oscillate up and down and up and down and up. But that oscillation narrows. That oscillation focuses on a y value of 2. 2. So as x approaches 1 from the left, the y values go to 2. As x approaches 1 from the right, the y values go to 2. They match. Since the left-hand limit and the right-hand limit are the same, then the regular limit is 2. Sometimes limits don't exist. So how about this? The limit as x goes to 3 of f of x. Well, this doesn't exist because the left and the right-hand limits are not the same number. As I go from the left, the y values approach 3, and as I move in from the right, the y values approach about 1.5. 3 and 1.5, these are different, so the regular limit as x approaches 3 does not exist. Here's another example where a limit does not exist. What happens now if I let x approach 3? Well, from the left, if I let x approach 3 from the left, what's happening to my y values? Those y values get bigger and bigger and bigger and bigger forever and ever and ever. Those y values never settle in on any particular number. And the same thing if I approach 3 from the right. My y values get larger without bound. The left and right-hand limits are not numbers. They don't actually approach anything. So here's another situation where we say the limit does not exist. One last example. In this example, neither of the one-sided limits exists. What's happening as I approach 0 from the left? So my y values are negative, and then they get a little more negative down to -1, and then those y values start oscillating wildly between -1 and +1, and they never settle in on any particular y value. They always are forever bouncing back and forth between -1 and +1. And the same thing if I approach 0 from the right. Those y values oscillate wildly, they never settle in on anything, and so the limit as x approaches 0 of f of x does not exist. We've been looking at limits graphically. Let's consider a numerical approach to limits. So a function is given to us, f of x equals the square root of x minus 1 over x minus 1. And what is the limit of this function as x approaches 1? If I imagine the x values in here getting closer and closer and closer to 1, this whole expression, what does it become? What number does that become? I wish I could just plug in 1, but I can't just plug in 1 because then my denominator would be 0. So here's what we do. We actually just plug in a bunch of values into the calculator, 0.9, 0.99, 0.999, 0.9999, and these numbers I'm plugging in are getting closer and closer to 1. And they're doing it from the left. Do you see that? These values are increasing. And as as the x values increase, getting closer to 1, it looks like these function values are getting really close to 0.5. And if I go the other way, now that's the one-sided limit from the left. How about the one-sided limit from the right? Now this table is a little bit upside down. Read it from bottom to top. 1.1, 1.01, 1.001, 1.0001. I'm approaching 1 from the right. And as I do that, these function values are getting closer and closer and closer to 0.5. So as I approach 1 from the left, the function values look like they are approaching 0.5. As x approaches 1 from the right, it looks like those function values are approaching 0.5. Since those are the same number, that is a great thing to see, then the unadorned limit, the regular limit as x approaches 1 of my function, suggests that the answer is 0.5. Let me show you how to actually do this on your calculator. There are a couple homework problems that will ask you to do a calculation like this. So, here's a photo of my TI-83 Plus. It is very old, and so your display probably looks better than mine, but here's what it looks like. So the first thing you need to do is push the y equals button and enter your function. Now, it's important with, so this is the function that we just looked at, square root of x minus 1 divided by x minus 1. If you have an old display like mine, it's really important to put parentheses around the numerator and parentheses around the denominator. Don't forget that. So many times I have seen students struggling to get the right answer, and that was the problem. They didn't put parentheses around the numerator and denominator. Okay, so you've entered your function. The next step is to go into Table Set. Okay, it's above the window button. And the only important thing there is set your independent to ask. By default, it's set to auto. You don't want auto. You want your independent variable to be set to ask. All right, now you're ready to make the table. So select Table, that's above the Graph button. And you can start entering values in the left column under x. This is why it was the ask for the independent variable. So you can just plug in any number you want. And as a result, in the column to the right of that, you will see the y values. Those are the values that come out of your function. Now, there's one warning, that these values that you see for the function values, those are rounded. So when I plug in 0.9999, the function value isn't exactly 0.50001. It's something more than that. In order to see the full value, you must move the cursor over so that it highlights the column. It highlights the number you want to see in the middle column. And down below, you can see the full value of the function. On some homework problems, they say, give us the answer to 4 decimal places or something like that, and you might have to do this in order to get the correct answer and round appropriately. All right, so we've seen limits. We've seen one-sided limits, we've seen regular limits, and we've mostly looked at them graphically, but we've also taken a numerical approach as well. And this concludes section 2.2.